Welcome to this video. My name is Mark Scythian. The date today is September 15, 2024. The title of this video is Polymerase Chain Reaction PCR Synthesis. So PCR synthesis is primarily implemented in the disciplines of chemistry and biochemistry. Its number one application is forensic science and crime scene investigation. PCR synthesis is a system to copy and or clone or chain react trace biological evidence. So it behaves sort of like a biological xerox copy machine. And so when set at 38 to 45 cycles, there's a ratio metric 400 to 600 fold copy factor for the smallest biological trace evidence. And so usually when you have a very small amount of biological evidence, the testing process itself destroys it. So in a crime scene, you're dealing with two types of evidence, the individual or the class evidence. So individual evidence is very potent. It's actual physical evidence. And so it's very hard to actually get living DNA off, let's say, a hair strand, but there's a higher probability almost dried blood splatter may have some living DNA. So that entire region is extracted without disturbing the sample. So if it was a splatter of dried blood on, let's say, the wall or the drywall, the entire piece would be cut out and it would be placed into the PCR testing through the proper chain of custody transport, and all the non-biological material would be inert during the process, but the biological materials such as 1 or 2 or 10 or 1,000 remaining DNA molecules would actually copy themselves ratiometrically on a 400 to 600 fold reduction of chain reacted samples. So that's about 38 to 45 logarithmic cycles in the PCR synthesis setting or the substrate setting. So the prohibitions on PCR as if we were testing, so there's nothing to test. You have the biological sample, you're just trying to copy and make more of the sample. So when you go to test it and unwind the nucleotides and the DNA molecule, you can test it incrementally by differential isolation. So in other words, if you tested the first 10,000 DNA molecules for blood type, and then you could test the next one for halotype, then mRNA, then mitochondrial DNA, until you put the whole picture together and you have some base, repeatable, incontrovertible evidence. But you can't get into the really detailed roots of DNA without statistical analysis, and that's when it could be argued as unprobable or probabilistic at best. But there's certain things you can validate with DNA sample if you find a trace evidence. So all the stuff you see on CSI is a little far-fetched. It's a little more entertainment, but when it comes to actual science and engineering and you have to extract a living DNA molecule, let's say a crime scene, then it is a very slippery slope to actually find a living sample. And so that's very important for a case, a prosecution's case. So the handling of that has to quickly go into PCR. So whatever biological samples that are found, they're copied into many, many, many more samples, so that when you go and do differential or isolation testing, you can, with absolute certainty, actually unwind all of the nucleotides in the DNA and get some accurate metrics that are very repeatable and very broad. So at least the RNA, mitochondrial DNA, blood type, and maybe the sequence order could be validated. And that could be just enough evidence to take it to the class or the circumstantial evidence. And so that's why PCR is very useful in forensic science and crime scene investigation, but it's also good for other industries, especially agriculture, where you need to get some trace DNA compounds that you found in a germination that don't belong there, and you have an ability to make enough copies of that foreign biological DNA sample and then get to the bottom of where, why, how, or maybe it was just transport mistakes, like some seeds were dropped, and you can actually validate that pretty quickly with PCR. But there are some prohibitions. You wouldn't want to use PCR as a test. So it's PCR synthesis. It doesn't say PCR test. It says PCR polymer chain reaction synthesis. So if you actually wanted to use it for like a test of some sort, you definitely would not want to use a PCR system for medical screening and viral tests, because obviously it would be inaccurate. It's the wrong test. And why? Because there will only be false positives or false negatives. So if you have a greater viral load than actually, let's say you have to reach 7 on a scale of 10 ratiometrically to test positive, but you only really have 3. If you use the PCR, it will clone so many copies of the viral sample that you might test at 8 when you're actually at 3, so you end up getting a false positive. Or the opposite can happen. Healthy cells or healthy DNA molecules or the non-targeted DNA molecules may also fall into the substrates, and depending how the test is calculated, you may have more healthy cells than you actually have, and then you end up getting a false negative. You're actually positive, but you test negative. So don't want to use PCR polymer chain reaction synthesis for any type of medical screening, because you're disturbing the original sample. You're getting more than you actually have. So usually false positives occur with the PCR used in medical and viral testing. And so the last part of this lecture is the STEM university student. So everybody who is a science, technology, engineering, and mathematics graduate, Bachelor's of Science graduate, has had at least 2 chemistry classes where part of their lab assignment was to use a PCR device to get enough samples of trace evidence or trace samples to complete a chemistry assignment, because most of the testing, as you isolate DNA nucleotides, even chromatography, the old school test, you will destroy most of the samples. So you can posit or elect to take isolation and differential testing. So you might take an X amount of DNA molecules for just one subtest, and then another subtest until you've built a genetic profile that's integrated. And so you come to a certain coefficient and number. So science is nothing without mathematics. So you want to do fact checking, it's all mathematical. There's no such thing as non-mathematical fact checking. So you're looking for differential rates of change, and then a area under the curve integration calculus to then find the linear coefficient. And so none of this is a summation. It is different nonlinear dynamics that then create an order. So we're going from a chaotic to an ordered integration under the curve, right? So that is what all the sub-testing is. And PCR is great because you don't have enough of the sample by design. The real world, you're not going to get all these samples. So first step, or I'll call it step number 0, is to implement PCR to reproduce enough of the trace samples or the small samples so you can do all these tests with confidence without worrying about destroying the whole sample set. So that's what every STEM major, only 2% of the American adult population are science, technology, engineering, and mathematics graduates. So, it would probably be easy to mislead 98% if somebody got in there and started telling people that they should have a PCR test for medical or viral screening. And, it's all money and politics on that end, but nobody in science, engineering, mathematics, technology would, that would be insane. Like, are you crazy? Do you want to make it so everybody's positive when they're not? So that's what the PCR polymer chain reaction synthesis used as a test would do. Just a xerox copy machine for biological samples. So all majors have used PCR in chem lab assignments, all STEM majors that is, and so that's chain reaction, xerox copying trace bio samples. And why? Because you want to preserve enough DNA so that surplus samples remain after the destructive testing process. And so that's kind of how things have been since at least the mid-70s when the test was, or I keep saying a test, it's not a test, it's a polymer chain reaction synthesis, it's a system. So when this system was invented in the mid-70s, it was then used for all sorts of field and lab tests, and that could be in both the science and engineering fields, or it could be in any scientific field that involves DNA molecules and making more of them so you have enough samples to do competent testing. So anyway, thank you for watching this video and have a great day.